Hey y'all, today we're going to be talking about volumes of revolution, or what we call revolving solids. This is another way that we can find volume. Last class we talked about volumes of known cross sections. This class we're going to find volume by revolving these spaces around an axis. It actually creates a cylindrical space, and it's really, really cool. So if a region in the plane being like the coordinate grid, is revolved about a line being our axes, the resulting solid is a solid of revolution, and the line is called the axis of revolution. So think about it as if we were literally spinning some flat piece of something around an axis, then it's going to create this 3D cylindrical shape. Okay? And most of those shapes, despite whatever our base is, are going to end up being kind of disc-like in nature. If I wanted to find the volume of the disk, I would do the area of the disk times the width of the disk, which of course the area of a disk, which is just a circle, would be pi r squared. Pi r squared. And then the width of the disk would be the width. So from this came what they call the disk method. The disk method is one of our two methods of finding the revolution of solids we're going to talk about today. Disk method comes from where it's a connected disk. So the circle doesn't have any holes or any weirdness in it. And it came from the same idea of pi r squared, so the area of a circle equation, and then times the width. So for our horizontal axis of revolution, it's r of x, vertical axis of revolution, r of y. This should feel similar to when we were doing our cross sections, where it was perpendicular to x or perpendicular to y. Okay, so horizontal axis, it's an r of x equation. Notice that's pi, r standing for radius, squared, and then w is the same as dx, because multiplying by the width is what we're doing when we're actually integrating. Okay, so all we're doing is we're integrating that circle equation, that area of a circle equation, which is giving us volume. Okay, so to help you out as well, r of x, the radius, is equal to top minus bottom, just like it has been for all of what we've done so far in chapter 7. And then r of y is equal to right minus left. And of course, it's the exact same equation, just with r of y and dy instead of r of x and dx. Okay, let's actually look at an example. So number 1, we want to find the volume of the solid formed by revolving the region bounded by the graph of f of x equals square root of sine x and the x-axis about the x-axis. Okay, so one thing I want to point out to you is all the ones we're going to be doing today, we're revolving around the x or y axis. The x or y axis, okay, x-axis, don't need x dash, x-axis, its equation is y equals 0. Y-axis, its equation is x equals 0. So anytime we're talking about revolving about the x-axis, think about it as your bottom equation or your left equation is going to be that x equals 0 or y equals 0. Okay, so we're revolving about the x-axis. So since we're revolving about the x-axis is a horizontal line, which means this is a horizontal axis of revolution. And we're revolving this space bounded by the x-axis y equals 0, and the function f of x is equal to the square root of sine x. Okay, so I'm revolving it about that x-axis. I'm spinning that. Kind of looks like a semicircle, but it is the square root of sine, so it's half of a sine function. I'm spinning it around that axis, so it's going to create a cylindrical shape. It's not going to be a perfect sphere, but it is a cylindrical shape. Probably end up more football-esque in nature. But let's talk about actually how to find these. It's really the same kind of idea as what we did last class, where we found the area equation, then we set up the integral, and then we went from there. So the first thing we're going to find is we're going to find our radius equation. So my first step is to find r of x or r of y. Okay, depending on which one I'm working with. My second step is to define my interval. And then my final step, once I have my r equation and once I have my interval, is just set up the integral. And then, of course, step 4 is to actually integrate. So very similar to what we did last time. Okay, so let's talk about number 1. We want to find our r of x equation or our r of y equation. So r of x is top minus bottom. So our top is the square root of sine x. So r of x is equal to the square root of sine of x minus our bottom equation is 0. So minus 0, which just means r of x is equal to the square root of sine of x. Okay, second thing we want to find is our interval. That's our step 2. Our interval, they tell us, is 0 to pi. So 0 to pi. All right, step 3, we want to set up our integral using r of x in our interval. So the pi times the integral. So we do have to make sure when we're doing revolutions of solids that we multiply by pi in the front. So pi, integral from 0 to pi. And then it's r of x squared. So parentheses, square root of sine of x squared dx. Okay, and just like last class, y'all, you could simplify this one pretty easily. Yes, square root of sine x squared, that would just be sine of x. Integral of sine of x is negative cosine of x, and then I can plug in from there. So that's a pretty relatively easy integral to do by hand. But you can also do this in the calculator. So if we did it in the calculator, I would just type it straight in. So second pi math 9 integral from 0 to second pi, not exactly, and then second, not second yet, parentheses, second square root, sine of x, close parentheses, squared, and dx equals 6.2831, which coincidentally is about 2 pi. And that's our answer. So revolutions of solids, they're really not too crazy, okay? Like I said, it's kind of the same process as cross sections. You're just plugging into a different formula. You're plugging into that area formula because we're rotating around and creating that cylindrical shape as opposed to one of those various cross section equations. All right, y'all, let's look at number 2. So number 2, we want to find the volume of the solid generated by revolving the region bounded by the graphs y equals 2x squared, y equals 0, and x equals 2 about the x-axis. So I'm just going to add in one little extra line here that we don't currently have, which is x equals 2. And that creates our nice little region here in the middle that we're going to be revolving about the x-axis. So still revolving about the x-axis, so still a horizontal axis of revolution, which means everything's going to be in terms of x with y equals equations. So first and foremost, we want to find our r equation. So step 1, r of x is equal to top minus bottom. So the top equation is 2x squared. The bottom equation is 0. So 2x squared minus 0, which just means r of x is equal to 2x squared. Step 2, we want to state our interval. We're looking at an x interval, so it's going to be from 0 to 2. Step 3, we want to set up our integral. So pi times the integral of 0 to 2. You will miss these if you don't include the pi of 2x squared squared dx. And then step 4, we just want to go ahead and integrate. So using our calculator, math 9. Oop, don't forget to put pi in the front. There we go. 0 to 2. Parentheses 2x squared. Close parentheses squared. And then dx. Notice, y'all, that I do have to put parentheses on the inside of the set of the parentheses for the integral. That is important. You can't use the parentheses that come with the integral if you need to square something or something like that. Then we get 80.425. And of course, if it was, because once again, this is one that we could definitely integrate by ourselves. So if we take out the pi, let's see if we get a nice pretty number. That's a pretty good one. So it is also 128 pi over 5. So you can always not multiply by the pi until the end if you need to leave pi in your final answer, which they'll either state that or it will be a multiple choice question and you'll see all the answer choices in pi. So either or. All right, y'all. Let's look at another one, number 3. All right, find the volume of the solid generated by revolving the region bounded by the graphs of x equals y squared, x equals 0, y equals 0, about the y-axis. Okay, so we're now revolving about the y-axis, so things are just a little bit different. So just to make things a little easier, I'm going to add in a little curve for us real quick. And x equals y squared is going to start here at the origin. It's just like a normal parabola. But just on its side. Oh, that is a very sharp looking parabola. We're going to make it a little less sharp. And then, of course, we have the lines x equals 0. X equals 0. X equal or y equals 0. And y equals 1. All bounding are not the greatest, mind you, graph. And of course, you can graph this on your calculator. You don't have to graph this by hand. And so the little area we're talking about is this little triangle that we're going to be revolving about the y-axis. So it's going to kind of create a cone-ish shape, but still being formed from that disk. Okay, so let's talk about this one a little bit more. So we're revolving about the y-axis. So now instead we need x equals equations, r of y, y interval, all that sort of stuff. So step 1 is our r of y equation. So r of y this time is going to be right minus left. So the right equation is y squared minus the left equation, which is just 0. So r of y is equal to y squared minus 0. So r of y is equal to just y squared. Step 2, we're looking at a y interval, which would just be 0 to 1. Step 3, we're writing our integral. So pi times the integral from 0 to 1 of y squared squared dy. And then last but not least, step 4, we're just plugging that integral in. And once again, y squared squared, that's just y to the 4th. That's pretty easy to integrate by hand, but we can, of course, type it into our calculator. So I'm going to show you without pi first. So math 9, 0 to 1. And remember, even though we're integrating y, we can still use x. So x squared dx. If it makes you more comfortable, you can, of course, type in y. It's just a little alphanumeric character for 1. So we do get 0.2, or about 1/5. So equals 1/5 times pi would be pi over 5, or if we multiplied 1/5 by pi, we would get 0.628. All right, y'all, and that is kind of our basic disk method. The next method we're going to talk about is what we call the washer method. And what makes the washer method unique is that the area, or the base that we're working with, isn't going to be fully touching the axis that we're revolving about. So this is where, with disk and washer, you really have to be able to know the difference between the two, which one we're actually looking at, which one we're doing. Okay. So if you notice with disk, the idea is that we're always on the axis that we're spinning around. Okay. With washer, as you can see here, notice how, like, if I was revolving about x or y with this curve that we're looking at here, it wouldn't be touching the entirety of that axis. So the whole one side of the base needs to be on the axis you're revolving around for it to be disk method. If it's not, then it's washer method, because it's going to create, when we spin it around, it's going to create a little bit of hole on the axes. Okay. So because of this, we now have to actually think about 2 radiuses instead of 1. So our equation that is further away from the axis is what we call big R. Our equation that is closer to the axis is what we call little r. And so our area in between is actually going to be big R minus little r. Well, that X didn't turn out too great, so we're going to redo it. So we end up with these two. We're actually taking the big ol' area. So if we revolve that whole outer function, so it's kind of like we're doing the disk method, and then we're taking out, we're like carving out little r. We're carving out the inside region to get that region just of the outside. So with washer method, notice that now it's big R minus little r, and the big thing is that we're squaring both of them individually, because like I said, it's really like we're integrating 2 disk methods, and we're just taking the smaller one out of the bigger one. So we need to square them separately. It's not one big squared, they're squared separately. That's very, very important to remember. Okay, and then same idea, horizontal axis r of x, vertical axis r of y. So for washer method, it's the same steps. It's just on the very first step, instead of just finding r of x, we're going to find big R and little r. So number 1, we want to find the volume of the solid form by revolving the region bounded by the graphs of y equals square root of x and y equals x squared about the x-axis. Well, this is y equals square root of x, and this is y equals x squared. So big R is always going to be the one that's further away from my axis of revolution. My axis of revolution in this case is the x-axis, so it's right here. So further away is going to be that square root of x function, or you can kind of think about it as like most on top. Okay, so the most on top would be square root of x, then x squared is in the middle, and then your axis of revolution. Okay, so big R of x is equal to still top minus bottom. The bottom is just our axis. So square root of x minus 0, so just square root of x. Little r of x, it's that inside function. So x squared minus the axis still, so minus 0. So then just x squared. Step 2 is our interval. It's an x interval. We can pretty clearly see it is 0 to 1. Step 3 is writing your integral. So the integral, pi times the integral from 0 to 1 of big R squared minus little r squared. So square root of x squared minus x squared dx. And then step 4, we just go ahead and plug it in and evaluate. And same thing as last time, y'all. I'm going to show it to you without the pi, and then I'm going to show it to you with the pi. So math 9, integral from 0 to 1. Second square root, nope, wrong thing. Parentheses, second square root of x, parentheses, squared minus parentheses, x squared dx. So that gives us 0.3, or about 3/10. And then, of course, we want to multiply it by pi. So we would get 3 pi over 10. Or if we actually multiplied it out, .942. All right, that's really washer method in a nutshell. Okay, I don't want to make this video too long, so what I want you to do is go ahead and pause me. Try and do number 2 and number 3 on your own, okay? And then you can unpause me and check me at the end, okay? All right, y'all, so just checking in on number 2. We see our bottom function is y equals x squared. Our top function is y equals 4x minus x squared, which makes our big R 4x minus x squared minus 0, and our little r x squared minus 0. So we just get each of those functions. Our interval is going to be an x interval, so we're integrating from 0 to 2. Plugging into our equation, pi times the integral from 0 to 2. Big R squared, so 4x minus x squared minus x squared dx, which then gives us 32 pi over 3, or 33.510. Okay, last but not least, number 3. This one had a little bit of a trick to it, okay? So we're revolving about the y-axis instead of the x-axis, so we're looking at an r of y, right minus left, y interval. But if you notice, our y intervals are really gross, okay? They don't hit at nice, pretty numbers. So remember, just like we did back in area between the curves, we could either solve for this in the calculator, which is totally okay, or you can just set the two functions equal to each other because they're both equal to x, so 3 minus y squared equals 1. Solve out for those y values where we intersect, and we get y is equal to positive or negative square root of 2. Then our furthest right function is 3 minus y squared, so 3 minus y squared minus 0. Left function is 1, so 1 minus 0. For big R and little r, interval is negative root 2 to positive root 2. Integral is pi times the integral from negative root 2 to positive root 2. Of 3 minus y squared minus 1 squared, lots of squares, dy, and then it's the gross one. We can't even get a nice pretty number with pi, so we just get 42.652. Okay, so y'all, that is Revolutions of Solids Day 1. We're going to talk about ones that are off the axis next class, which really isn't anything too crazy, but hopefully this was a good kind of preview, and we're just about done. We got 1 day of notes left, but I'll see y'all in class.